So I put it far away from because my voice is a little bit loud. So we're going to begin the morning session. I want to welcome everybody back. Okay, then we have now the correct one and everything's good. So we have the first keynote speaker today, and then afterwards, after the coffee break, that we will have, if you know, is the bar, it's the second bar from in this plaza, that we will walk through that door later. Okay, so you're going to get lost. Not that you will need coffee after, Axel's talk. Yeah. And then we will continue with the morning session. So I'm Jairo Sinova, and I'm replacing Oliver Klein, that could not be here as a discussion leader today due to family reasons. So we'll start today, the first one with Axel Hoffmann, who is now in Illinois, previously in Argonne National Lab, and he's going to tell us lots of things about spin currents with antiferromagnets and how they're going to change the world.
Thank you, Jairo. We'll see about changing the world, but maybe there's at least something interesting. And since the topic, one of the main topics of this conference was supposed to be antiferromagnetism, I think it's a timely thing. So I'll tell you a little bit about the things, how we were dabbling with spin currents and antiferromagnets lately. Okay, so here is what I want to tell you. I'll have a brief introduction since it's like the first talk of the day about spin transport and spin-orbit coupling. Then I'll tell you a little bit why we're interested in metallic antiferromagnets. And then I'll tell you some of the things that I find interesting about it. Like the first thing I'll tell you about something that we see some magnetoresistance in these antiferromagnets. Using these antiferromagnets that's unidirectional, which is kind of unusual because you think of antiferromagnets being always, having two symmetrical directions in a way. Then I'll tell you a little bit how the symmetry considerations of these antiferromagnets may play a role, how the fact that you have magnetic order gives rise to new interesting effects. Building on that, I'll talk a little bit about magnetic spin Hall effects, and then I'll tell you also something that's missing here, how we can use these new spin orbit torques that we can get because of the magnetic order in these antiferromagnets for driving new dynamics. And then I have some brief conclusion here. Okay, so we've already heard a very nice presentation yesterday from Albert Fert, who is certainly one of the people that got us started thinking about spin transport in new ways. And essentially, when it comes down to spin transport, the important thing is, if you look at the typical ferromagnetic band structure here for like a transition metal, ferromagnet, iron, nickel, cobalt, something like that, you have exchange split D bands, and because of that, you have different density of states at the Fermi level for spin up and spin down electrons, and that gives rise to different spin mobilities and density of states. And that is then reflected in that the charge transport becomes now also dependent on the magnetic structure, essentially. And this all started in earnest with the discovery of giant magnetoresistance in the late 80s, and a decade later, tunneling magnetoresistance also was discovered. And the basic idea there is you have several layers, and by having a layer in between, either a normal metallic layer in the case of giant magnetoresistance or insulating tunnel junctions, you can then have different resistances dependent on the relative orientation of the magnetizations. And most of us are very familiar with this idea. And then about 10 years later, the opposite idea essentially took hold, that we can use spin transport to manipulate magnetization states. In fact, this idea was already developed both theoretically and experimentally before the discovery of giant magnetoresistance. But really, it started becoming important when we were able to make nano contacts where we can have very high current densities, very high densities of spin polarized currents injected into a ferromagnetic layer. And this gives rise to spin transfer torques, whereby injecting a spin polarization into a magnetic layer, the spin polarization injected into this magnetic layer can then interact with the magnetization and reorient the magnetization. And this is now the basis for a lot of devices, how we manipulate magnetic states in real applications. And so there essentially are two types of spin transfer torques. The first one is what you saw in this sketch earlier, that you inject a spin polarization, and the spin polarization will then precess around the magnetization that you have in this ferromagnetic layer. And so you lose the transverse component of the spin polarization, which gets transferred to the magnetization. And if you work it all out, that becomes like a damping-like torque, meaning it's a mechanism by which you can really change the energy of the ferromagnetic magnetization in your ferromagnet. But also the opposite is possible. You can have the spin polarization injected, and then the ferromagnetic magnetization precesses around the spin polarization that you inject. And in this case, you have what's known as a field-like torque. And in general, you can think of that the damping-like torque is dominated if the spin polarization is generated non-locally, like in the spin transfer torque picture, where you have the spin polarization generated in one layer, then injected into a different one, or in spin Hall effects, where you generate spin currents far away from the interface, but then you have a spin accumulation due to the boundary with the ferromagnet. While these field-like torques are mostly generated when the spin accumulation is generated locally, like directly at the interface through a Waschbar-Edelstein effect or something like that. And of course, in reality, both is possible, and no matter which spin generation process you look at, you have probably a mixture of both to some extent. But if it's locally, it's probably mostly field-like. If it's non-local, mostly damping-like. Okay, so over the last decade or so, we figured out a way how we can generate spin currents for spin transfer torques even more efficiently than by generating them non-locally through exchange interactions from a different layer. And so this idea is known as spin orbit torque. So you can use some spin-dependent scattering, like spin Hall effects, which separate different spin directions towards different interfaces in a layer. And these give rise to spin accumulations that can then inject it into the ferromagnetic layer and give rise to spin torques, just as in the traditional way how you do spin transfer torques. And there are some geometric advantages of using these torques, because now the interfaces through which the spin current goes and the cross-section through which the charge current flows can be vastly different. And that helps to give rise to quite some amplification of how much spin current you can generate by the charge current. And so in terms of being energy efficient, as what we heard yesterday from Albert, that has huge advantages. Okay, just a brief back on the envelope kind of calculation. If you look at spin transfer torque MRAM, where you generate spin torque in one layer, inject it into the other one, I'm not going to bother you too much with the details, but if you plug in typical voltage that you want to use to operate these devices and a typical resistance area product, you get a power density of the order of this, 0.6 megawatts per square centimeter. If you now use spin orbit torque for switching the magnetization, and you use, again, typical parameters that you find, like a switching current density that's quite reasonable, and resistances for your layer, then you immediately see that you get power densities that are at least 1 to 2 orders of magnitude lower. So in order to be more energy efficient in switching the magnetization, spin-orbitals have some real advantages. And also, as was already mentioned yesterday by Albert, since you have smaller current densities or currents in general, you can have a higher overdrive, which means that you can also switch things faster because you're much further away from current densities where you structurally damage your device. Okay, so with that introduction in spin currents and in general, let's now focus on metallic antiferromagnets. So far, I haven't said anything about antiferromagnets. Right? So antiferromagnets, metallic antiferromagnets, are interesting because they can also generate spin currents through spin Hall effects, just like any other non-magnetic or even ferromagnetic material. You can have this spin-dependent scattering no matter what it is. And early on, we already noticed in manganese-based metallic alloys that these spin Hall effects can be quite large, similar to what we do if we use platinum, which is one of the main materials for generating spin orbitals. But more interestingly, shortly thereafter, it was shown that certain antiferromagnets, the antiferromagnetic structure can interplay with the local structure in some curious ways. Like here's an example called copper manganese arsenide, where the two sublattices of the antiferromagnet have locally opposite inversion symmetries. And that gives rise to essentially opposite electric fields, which gives rise to opposite spin-orbit coupling phenomena. And so you locally generate spin accumulations that are in the opposite direction. So they have the same staggered geometry as the magnetic structure. And so that then allowed to electrically, possibly, switch the magnetization states. So in these materials, there's still quite some discussion. How much is really due to spin torque? How much is related to heating and other things and what have you? But there are other examples like non-collinear ferromagnets like manganese 3 tin, where it's pretty clearly shown that you can use spin orbitals for switching magnetization states. So this became quite interesting because now we can electrically manipulate magnetization states very similar to what we've been doing in ferromagnets. Okay, so I already pointed this out. There are some magnetic metallic antiferromagnets where the magnetic structure actually has some profound impact on the electronic structure, where you get some non-trivial band structure where they become topological semi-metals, wild semi-metals. For example, here's an example for manganese 3 tin, where you then have wild nodes in the electronic band structure, which their position is related to the magnetic structure, the way how the magnetic structure breaks the symmetries in these materials. And so again, there's a lot of interesting interplay there. Okay, so let me go back to this first point. I wanted to briefly mention that spin Hall effects in antiferromagnets can be rather large. Here is an early work from us on this, where we looked at different antiferromagnets, manganese alloys, going from 3D metals to 4D to 5D metals alloyed in there. And not so surprisingly, as you go to the heavier elements being in part of the alloy, you get stronger spin Hall effects, because the platinum simply has more spin orbit coupling than the iron. And in fact, you get spin Hall effects that are very similar to platinum itself. So we can also understand these spin Hall effects simply by the band structure of the antiferromagnets. If you theoretically calculate the spin Hall conductivities, they're actually very similar to what we measure experimentally. There are some discrepancies here, which mostly have to do that in the theory they use a different spin structure, which is probably not quite realistic for iron manganese. But so this is not so surprising, very easily understood. Now, but since the spin Hall effects can be big, we can have large spin Hall spin accumulations in these materials. And since the other main topic of this conference is light or X-rays, so Stefano likes a lot of X-ray experiments. I thought I'd put just one example what we can do. Namely, you can use X-rays to directly look at spin accumulations in materials. And so this is some work where this was done for copper, where using a copper nickel cobalt multilayer, you injected spin accumulations into the copper. So these were samples that Andy was involved with. And indeed, you can see then by looking at the dichroism at the copper edge that you get a spin accumulation in this copper. Now this is a heroic experiment in some sense, because you see it's in the 5th digit where things are changing. So it takes quite some effort. But I wanted to show you that with platinum manganese, we have a case where the spin Hall effects are very big, and at the same time, for those folks that do X-ray experiments, we have the manganese L edge conveniently available to look at spin accumulations. And sure enough, we made a structure here where we split the current in 2 directions. So in a spatial resolved image, we can look at the spin accumulation with opposite signs easily. And lo and behold, we do see at the manganese L edge a change when we put a charge current through the platinum manganese, which scales with the current density. And if we analyze this quantitatively, we actually get spin Hall effects that are very comparable to what we measured with transport. So, so you can directly image the spin accumulations in these materials now. Okay, so now I wanted to tell you a story that is somewhat surprising. Namely, we looked at some of these antiferromagnetic materials, and we discovered a magnetoresistance that's unidirectional. And at first, that seems kind of counterintuitive. So let's first think about how magnetoresistance looks like. So here's an example, let's say for iron. And so here you see the resistance change in 2 perpendicular directions for the magnetic field, normalized as a function of the direction of the magnetic field. And you see that the resistance is high here, 90 degrees. When you change the magnetic field 90 degrees to it, the resistance becomes low. Then it becomes high, identical, once you would completely reverse the magnetization, and then it becomes low again. So this simple cosine squared dependence. So this has been known for a long time, and it's been used in the old days for detecting magnetization in hard drives and all that. Now, the nice thing is, this effect is even in the magnetization. So in some sense, you would also expect it in antiferromagnets if you rotate the magnetization by 90 degrees. And sure enough, you see this in lots of antiferromagnets. Here's an example for copper manganese arsenide, which I simply picked because the curve looked very similar. So you see if you go to large enough field, you get the same kind of cosine square dependence. Now you have to be a little bit careful how the angle is defined. In the antiferromagnet, the magnetization is not aligned with the field, but you get the spin-flopped configuration. So you have like a 90-degree phase shift in the magnetoresistance typically. But overall, it looks very similar. And in particular, it's identical if you reverse the field by 180 degrees. So there's nothing that looks unidirectional in any way. Similar to the ferromagnet, where there was nothing that looked unidirectional in any way. So then we did some measurements with iron rhodium, which is an interesting antiferromagnet for lots of reasons, and I'll come back to that a little bit later. And we capped it with platinum. Now, you can probably guess that our main intention was to use spin orbitals from platinum to do something interesting with the iron rhodium. That didn't quite work out, but we stumbled across something else that's really interesting. Then we measured the magnetoresistance. So here is the change in the resistance as a function of angular direction of the magnetic field. And we saw that this magnetoresistance has now an additional cosine phi type term. So a contribution that changes sign when we reverse the magnetization. And that was really curious. Now, first of all, I have to say, in order to see this, you have to do this, with one current direction. If you reverse the current, you average things and this goes away. And so since most people measure things by reversing current, you may have seen something similar, but not seen it because you didn't look for it. Now, so that's curious enough on its own. But then when we look at the magnetic field dependence of this unidirectional magnetoresistance, it's quite surprising. Well, there's none at zero field. Well, that makes sense. At zero field, we're not changing anything. But then becomes negative for small fields and changes sign at relatively high fields, like 7 Tesla. That's a big-ass field. So that definitely got us scratching our head. What's going on here? It turns out that the story is relatively easy. So the first thing is, if you have some spin accumulation generated at the interface, and so if you think about interfaces, one of the first things that comes to mind is like Rushbar spin-orbit coupling. And I'll show you in a moment why we think Rushbar is important here. Then you can actually get something that's maybe unidirectional in some way, right? Because you generate a spin accumulation that's mostly perpendicular to the current, in the plane of the interface. And now when you apply a magnetic field, you rotate your antiferromagnetic moments, but you also cant them a little bit, right? And so if you reverse the field, the canting may be slightly different. I just noticed there's a mistake in this graph, but never mind. So this is for the current in the opposite direction. So we have now a spin accumulation and a net magnetization, and so the relative orientation, whether they are parallel or anti-parallel to each other, can give you something unidirectional, right? But where do we get this strange magnetic field dependence from? Okay, so it turns out that looking at the Rushbar effect allows to explain this quite naturally. So if you look at zero magnetic field, if you have a Rushbar effect, you get this spin momentum locked band structure with like 2 Fermi surfaces which have the opposite chirality of spins, the opposite polarization of spins in each case. Now, all that you need to do in order to understand the magnetoresistance effects that we see is that you have to think about how this Rushbar spin-orbit coupling electronic structure changes if it also interacts with the net magnetic moment that's generated by the antiferromagnet. Essentially, what happens is that one type of spins, let's say the ones that are pointing towards you, get lowered in energy, and the other one may get lifted up in energy. So you distort your parabolas kind of like this, And you increase the field, we increase the net moment from the canting, and so you change this distortion even more. And so instead of having nicely circular Fermi surfaces, you get now some egg-shaped kind of Fermi surfaces. And the two Fermi surfaces in the center and the outside one distort in opposite directions. So that actually allows you to calculate this field dependence of a unidirectional magnetoresistance that you may get from it. Essentially, each of these distorted Fermi surfaces, because of its asymmetric distortion, gives rise to an individual unidirectional magnetoresistance. These unidirectional magnetoresistance are opposite in sign because the distortions are opposite. But also, since the distortions are going to be different, right at this field, the inner Fermi surface actually starts kind of to vanish in a way because you shift the Washbar parabolas so far. It turns out that initially, the magnetoresistance of the inner Fermi surface dominates the overall magnetoresistance. But at high enough field, the one from the outer surface becomes dominant. And so you get this trade-off. And if you calculate this, you get something that qualitatively looks very similar to what we see experimentally. Now, it doesn't do it quantitatively well. There's some different structure. But here, we didn't take into account things like anisotropy in the ferromagnet and the antiferromagnet, which may change how much canting you get and all that. So for a very simple model, I think the agreement is quite nice. Okay, so we've seen how we can get some unusual effects by the way how the spin structure of the antiferromagnet couples to the electronic structure. And I want to expand on that a little bit more. Because one of the interesting things about antiferromagnets is that the magnetic structure that you have in the antiferromagnet can also break symmetries in very interesting ways. And these additional symmetry breakings can give rise to interesting spin transport effects. And so for this, let's think a little bit how symmetries play a role. If you have a material where there is some mirror symmetries, then that tells you how different vectorial quantities should change upon acting with these mirror symmetries. And it's complicated. You have polar and you have axial vectors. Polar vectors are like spatial directions. Under mirror symmetry, they reverse if they're perpendicular. They stay the same if they're in the mirror plane. And axial symmetries, vectors are things like magnetizations, which you think of being generated by rotating currents in a way. And there it's exactly the opposite. If you're perpendicular to the mirror plane, it stays the same, and it reverses if it's parallel. And so if you look at this, for the generic spin-orbit-torque configuration, where you have some normal metal, some ferromagnet on top of it, and we now totally ignore crystal structures and what have you, then you see, because of the mirror symmetry that's in the plane given by the current direction and the normal to the interface, that if you have magnetizations that are perpendicular to this mirror plane, there cannot be any torques. Because if you look at how the vectorial quantities should change, the torques should reverse. But they can't because it should be symmetric, so they got to be zero. So in other words, this means that in normal spin-orbit-torque configurations, we always get a spin polarization, which is this vector p, which is perpendicular to the surface normal and the current direction. Right? So this is very good if you want to put torques on magnetizations that are in plane, but if you want to have magnetizations that are perpendicular and switch them in a deterministic way, this actually doesn't work with these ordinary torques. Now, if you look at an antiferromagnet, because you have ordered magnetic moments, that may lead to symmetry breakings beyond those that you have from the crystal structure. And this was really very nicely demonstrated by some experiments done in Dan Wolf's group at Cornell, where they looked at manganese gallium nitride. And so this is an antiferromagnet that has a non-collinear spin structure, meaning you have spins pointing in all kinds of directions, which is nice because that breaks symmetries in all kinds of directions. So if you look in the non-ordered state, you have very high symmetry. It's a cubic material, so you have mirror planes everywhere. And so if you measure now spin orbitals, you get in the high temperature non-magnetic phase, essentially only spin orbitals that are along the y directions, and the ones along x and z are 0. But if you now go to lower temperatures, below the Néel temperature, you have all this ordering. There's only one mirror plane left, and you can easily make that such that it's not in the direction of the current. And now you can have spin accumulations both in the x and z component, and lo and behold, that's what they see when they order below the Néel temperature. Very beautiful experiment that demonstrates the role of these additional symmetry breakings. Now, in fact, you kind of, if we would have been clever about it, we would have noticed this maybe a little bit earlier, because when we worked on these manganese-type alloys, when we worked with our theory friends, they calculated, spin Hall configurations for different crystalline orientations, for the staggered magnetization in different directions. And lo and behold, you get like lots of different numbers. It's complicated. In the first experiment, actually, we had to make some wild assumptions how it averages all out. So we got the nice agreement I showed you earlier. But we were intrigued enough that if you grow the material along the c-axis or the a-axis, that you expect very different spin Hall effects. And it turns out that experimentally, you can actually easily grow these materials in these two different directions. You just change the growth temperature. In one case, it's z-axis oriented, and the other one, it's a-axis oriented. Just the difference in thermal expansion between the MgO and these manganese alloys. And lo and behold, on platinum manganese, we experimentally saw the same trend that for the a-axis grown sample, the spin Hall effect should be much bigger than for the c-axis grown ones. And the iridium manganese, it was exactly the opposite, as was also predicted by the theory. So that already told you that the symmetry breaking of the magnetic structure actually can have some very profound effect on what you see there. And so we saw something along this line in our old friend iron rhodium, which is interesting antiferromagnet. Part of it is because it can be both a ferromagnet and an antiferromagnet. You just look at whatever temperature you have. At high temperature, it turns out to be a ferromagnet. You have a high magnetization at low temperatures. The magnetization vanishes. This goes hand in hand with a big structural change and a big change in the resistive properties, like the resistance changes by a factor of 2, so you can easily narrow it down. So what we did is we grew epitaxial iron rhodium on MgO, put a little bit copper on top so we don't couple it directly to a ferromagnetic layer, and then had permalloy on top, and we looked at spin orbitals. And what we ended up seeing is that we saw spin orbitals that were in some unusual direction and very, very large, actually. Namely, the spin orbitals ended up with a spin polarization that was at a 45-degree direction with the current that we apply. So the first hint that something unusual happened was when we did spin transfer torque measurements, spin transfer torque ferromagnetic resonance measurements of these samples. So the first one is shown here. we have the field in a 45-degree direction because that allows us to see the biggest spin transfer torque ferromagnetic resonance signals. But it turned also out that the current was along a specific direction, the 110 direction, so that the field was along the iron-rhodium 100 direction. And when we looked at the mixing voltages as a function of field, we see this kind of change to the ferromagnetic resonance of the permalloy is right here. And for those of you that are spin torque FMR aficionados, there are always two contributions to the line shape. One is anti-symmetric, one is symmetric. The one that you typically get excited about is the symmetric one because that indicates large spin orbit torques. And in that respect, this looks very disappointing. There's hardly any symmetric component that indicates there's not much of a spin orbit torque there. But then we do the same measurement, and we add a DC current on top of it. So this you do to see if you have some damping torques that change your line width. And so you can measure the line width easily, from these measurements. And what we saw is that the line width changed quite considerably with DC current. So this tells us we have a really large spin orbit torque there. Okay, so wait a moment, how do we reconcile these two? Well, so once you start thinking about this a little bit more, you see that this measurement is only sensitive to the spin polarization that's perpendicular to the field, because that's going to give time-varying torques that drives the resonance. All right? Well, this measurement is only sensitive to spin polarizations that are along the field, because those are the ones that will actually change the damping. And so in your ordinary experiment where the spin polarization is perpendicular to the current, the two are more or less the same, because it's 45 degrees, and so you see the same thing in both measurements. But here, what this suggests to us is that the current-induced spin polarization is actually at a 45-degree angle with the current. So highly unusual in a way. Never trust just a single measurement. So we did another measurement where you are sensitive to these spin orbit torques. It's called second harmonic Hall measurements. Essentially, it's a DC variation of this spin torque ferromagnetic resonance. We use DC currents and see how the effective fields generated by these DC currents through spin polarizations then change the orientation of the magnetization. And you can do the full angular dependence of these effects. And what we saw from that is, I'm not going to go into all the great details, but if you fit this, again, it confirms a spin orbit torque that's large with a spin polarization that's 45 degrees to the applied current. So essentially, the thought is that when you have even a collinear antiferromagnet, what can happen is, of course, that the spin lifetimes parallel to the magnetization and perpendicular to the magnetization are very different. And so that difference in spin lifetime allows you to filter out whatever spin polarization you generate due to ordinary spin Hall effects or whatever it is, to be then mostly either parallel or perpendicular to the magnetization, and it depends on the details. Now, in our experiment, we can't necessarily tell whether it's, which direction it is, because we don't know exactly what the magnetization does. But one thing that's very interesting is, so these exotic torques at high temperatures just at those temperatures where we start getting antiferromagnetic orders are relatively small, but if you go to low temperatures, it becomes very large. So these spin torque efficiencies are of order 3. So it's like a spin Hall angle of 300%. This is humongous. So part of that may also be related that the electronic band structure iron rhodium as well. They're complex with wire nodes all over and what have you. Okay, so now that we've seen that the magnetic structure of the antiferromagnets can have a profound effect on the spin transport properties, I want to step it up a notch and talk about magnetic spin Hall effects. So far, we've only talked about how the breaking of mirror symmetries may allow spin polarizations that are in directions where you ordinarily don't expect them. But you can have something that's even more complicated, which is indicated here. So the ordinary spin Hall effect, as we said, it's perpendicular to the electric field or the current and within the interfacial plane. So if you have a wire and pass a current through the wire, you get spin accumulation that are kind of like the blue. But if you now have a magnetization that's parallel or antiparallel, then that can break symmetries in that direction. And now you can also have spin Hall effects that are, for example, perpendicular to the interface, but that reverse their sign when you reverse the magnetization. And it turns out that this is something that you actually see in antiferromagnets. Now, there's something else that's interesting. If you look at antiferromagnets, that the spin structure can directly influence the spin polarizations of the electronic band structure. And a really beautiful example is given by these non-collinear antiferromagnets, manganese-3 tin or manganese-3 iridium, are two examples of two of these types. They have slightly different winding of the antiferromagnetic order. But what it comes down to is that you can have now a spin polarization and the Fermi surface that is directly reflected of the orientations of the spin in these antiferromagnets. So you can have spins that rotate around like twice around the Fermi surface as you go. And so that means if you apply currents in this direction, you have a spin polarization, a net spin polarization of the current. And more interestingly, if you think about spin Hall effects, if you look at transverse currents, you see that the Fermi surfaces may look very different and their spin polarization may look very different. And so you can get then transverse transport effects, spin Hall effects, that are directly tied into the direction of the magnetization, and they reverse their sign as you reverse the magnetization. And depending on whether you have a structure like this, which would be for the manganese-3 iridium, or something like this, which would be the manganese-3 tin, in both cases you can have unusual spin Hall effects with polarizations that are either along the current direction or the spin current direction, which you normally don't expect. And this was actually very nicely shown by a Japanese group looking at manganese-3 tin, where indeed what they saw is here in manganese-3 tin, you have a small magnetic moment, which is too small to really play an important role in terms of polarizing spin currents or Kerr effects. But it's big enough that it allows you to reverse the magnetic structure with relatively modest magnetic fields. And so they saw if they reversed the magnetic structures that they saw spin transport properties. So here they have a potentiometric measurement where they use nickel iron as a spin-dependent voltage detector that reverses sign as you reverse the magnetization of the antiferromagnet, and then change the magnetization of the ferromagnet with fields that are too small to change the antiferromagnetic structure. And if they measured now the angular dependence of these effects, it's quite striking that you see things that become now even in magnetic field. So we got interested and looked at this with iridium manganese 3. And so here what we did is a very similar experiment to what we did earlier. So we have iridium manganese 3 permalloy. When we pass a current through the sample, this current does generate spin orbit torques, which changes the line width of the ferromagnetic resonance by changing the damping. So we are looking directly at damping-like torques. And we saw relatively large damping-like torques in these samples. So there are some intricacies about the directions of applying currents and fields, and I'm not going to bore you with that. But the interesting thing is that when we looked at the angular dependence of these current-induced changes of the damping, they again become even in the magnetic field. And so they have this angular dependence that you would not expect ordinarily, where normally you think your damping-like torque reverses sign if you have the opposite magnetization. So this is, again, indicative of having this magnetic spin Hall effects responsible for the spin orbit torques that you see here. So what we see now is by using the symmetry breaking that you can have in antiferromagnets due to their antiferromagnetic structure, you can get a whole lot of new spin orbit torques in new directions that really weren't accessible to us before. And if you paid attention yesterday evening, Albert Fair talked about the issue of being able to switch perpendicular magnetizations. This can be done now possibly in much more easy ways by using these materials where the symmetries are broken, in the bulk. Okay, so I want to give you one example what interesting things you might be possibly doing with these materials. And this is talking about multiple magnetic droplets. And I know it's unfair to change topics, you're so close to the end, but let me do it anyway. Magnetic droplets is something that generated quite some interest. Those are magnetization dynamics, and so Andre is like an example. If you really want to know all about droplets, ask Andre, not me. If you drive in a uniaxial ferromagnet the damping to zero, you can have a dynamic state where you have the magnetization reversed at some part, and you have magnetization precessing a full 360 degrees in between these regions. And so you can artificially do this by injecting spin currents. We've seen that spin currents can change the damping. You can use spin currents to drive the damping to zero. And so you can actually do this with perpendicular films. This is a cobalt-nickel multilayer. So this is from one of the first experimental demonstrations of this. And it's nice. There's a large precession angle, so you have rather strong magnetization dynamics and so on. Now, in these, using spin transfer torques, you only get one droplet at a time because you have some nano contact to get the current densities that are high enough, and so that's it. Now, what we ask ourselves is, can we use spin orbit torques instead of spin transfer torques to generate multiple droplets? Well, so the first problem is, okay, spin orbit torques are not so good, right? Because ordinarily, they only generate spin polarizations that are in the interfacial plane, so they don't change the damping of perpendicular magnetized films. So you can actually tilt the magnetization of these films, and then you can use spin orbit torques. That's been done, but that's kind of like the trivial way of doing things. So we were just interested, okay, let's assume we can tilt the spin polarization a little bit. Does that allow us to do something interesting? So we did some pandemic science, micromagnetic simulations. And we looked at a generic ferromagnet with numbers that are typically for cobalt nickel, let's say, and put it on top of a generic spin-orbit torque layer, which has a spin accumulation at some angle, with numbers that are reasonable compared to what we know from these manganese alloys. And so what we see, indeed, if we drive now a spin current, and we have a spin accumulation that's at some angle with the interface, that allows us to nucleate a droplet. The only problem is, once the current is large enough in the simulation to nucleate the droplet, if you let it go for a while, well, you get more droplets, so that's kind of interesting. The one in the center grew quite a bit in the meantime. Then you can get even more droplets, and then if you wait some time, all hell breaks loose, and you're not going to measure anything interesting. But, so fortunately, so we know we can generate droplets. They're just not stable at the current densities that you need to nucleate them. Well, so as often happens, the requirements for keeping something stable and for nucleating something may be totally different. So we looked at it and said, okay, how about we just have a short pulse and then a lower current to sustain the magnetization dynamics. And lo and behold, that works. That becomes stable, and it becomes stable on long time scales. And if we have a longer pulse, we can generate 3 droplets, and so they become stable. So indeed, you can, in principle, imagine doing this. And I see Jairo gets nervous, so I'll just want to say, we can then go and have some basic currents through the device, which keeps the dynamics stable. But then we have small pulses in opposite directions, and that allows us to add droplets, subtract droplets, and then you can look at, okay, how do the magnetization dynamics interact with each other and what. So maybe there's some very interesting things that you can do in the dynamics of these systems. Okay, so I'll wrap it up. There were a lot of people involved in the work. Many of you, or a couple of you in the audience may find your name there. Jairo, you don't need to look, you don't see your name, sorry. But the most important ones are the ones in orange. Wei Zhang is the one that started our work with metallic antiferromagnets. Jonathan Gibbons did the work on the spin-orbit torques in iron rhodium. Sahima Siddiqui did the X-ray experiment. Soho did the measurements on the unidirectional magnetoresistance. Robin did the soliton simulations, and Jose did the work on the magnetic spin Hall effects. So here are my conclusions. You can read them for yourself, and I'll be happy to answer any questions. Thank you very much.